Many different pieces of equipment, like pumps, compressors, and fans, are essential to the operation of an industrial facility. But before this equipment can operate, it must be supplied with power. Electric motors are among the most common means of supplying power to drive equipment. But other drivers, such as internal combustion engines, gas turbines, and steam turbines, are used in various applications. During the course of your training, you'll be learning about all these different types of drivers. For now, we're going to focus on steam turbines. Making sure that the turbines in a facility are working properly is an important operator responsibility. If the turbines aren't functioning properly, the driven equipment can't perform the work that must be done to keep the facility running smoothly. For example, this steam turbine drives a feed pump for a boiler that supplies steam to many different processes in the facility. If this turbine were to fail, it could affect not only the operation of the boiler it supplies, but all the different processes using the steam from the boiler as well. For reasons like this, it's important that operators understand how steam turbines work and how to keep them operating properly. In this program, we'll concentrate on the basic information you'll need to operate your turbine safely and efficiently. Let's start by looking at what a steam turbine does. Essentially, a steam turbine converts the energy contained in steam into mechanical energy that can be used to drive rotating equipment. We'll use a simple illustration to show the basic principles of turbine operation. The process is a lot like steam blowing on a fan's blades and making the blades turn. The steam first passes through a restriction called a nozzle. The purpose of the nozzle is to convert the steam's pressure into velocity. You see, as the steam passes through the nozzle, it speeds up. The faster moving steam then strikes a set of blades, causing them to turn. And the turning blades produce mechanical energy that can be used to drive rotating equipment. The blades used in steam turbines are a little different from the simple fan blades we just saw. Let's take a look at some typical turbine blades and see how they do their job. Generally, turbines use a series of fixed and moving blades to make the most effective use of the steam's energy and cause rotary motion. The blades shown here are designed for what is called impulse movement. Basically, impulse means that the high-velocity steam pushes on the blades and causes the blades and the shaft they're mounted on to rotate. We'll take a closer look at how impulse movement works in a moment. Turbines also have blading that does not rotate. There are a series of fixed or stationary blades here, attached inside the bottom half of the casing. Both kinds of blading, fixed and moving, work together to accomplish the energy conversion that takes place in the turbine. This example shows the blading arrangement in a typical small turbine. Two sets of moving blades are included on one wheel that is attached to the turbine shaft. The fixed blades here are located between the two sets of moving blades. Now, to get an idea of the flow path of steam through this arrangement and explain how this flow path causes movement, we'll use this illustration. In our illustration, the shrouding or rim that holds the blading together has been removed so we can see the shape of the blades. These are the moving blades, and these are the fixed ones. The steam flows through the first set of moving blades where some energy is extracted. From here, the steam flow is routed on to the fixed blading. The fixed blading then redirects the flow of steam to the next set of moving blades so that more energy can be extracted from the steam. Once the steam has passed through the second set of moving blades, the steam is routed out of the turbine. This flow path of steam striking the moving blades causes the moving blades and the turbine shaft they're mounted on to rotate. The energy in the steam decreases as it is converted to rotational force. So the steam now contains much less energy than it did when it entered the turbine. The arrangement of blading we just saw is typically referred to as a single-stage turbine. Like the example you see here, single-stage simply means that a series of fixed blades is used together with one or two sets of moving blades. In this program, we'll be focusing on turbines similar to this one. There are other turbines that are called multi-stage turbines. In these turbines, a stage refers to one set of fixed plus one set of moving blades. Well, we've covered some important basic concepts for steam turbines. We've talked about what a steam turbine is and about the principles of how a steam turbine converts the energy contained in steam into a rotational force. These concepts are the basis for all phases of steam turbine operation. So before you go on, review your text and make sure you understand the material that we've just discussed. Then, when you return, we'll take a look at some of the basic components of the turbine itself. We began this program by discussing the principles of what a steam turbine does, how it converts the energy from hot, high-pressure steam to a mechanical force that can be used to drive other pieces of rotary equipment that perform work. Understanding these basic principles is one of the first steps in learning how to operate a steam turbine. In addition, as an operator, you need to be able to identify the essential parts of the turbine you're working with and understand what each of these parts is designed to do during the various phases of turbine operation. For safe and efficient operation, every part of the turbine must be functioning properly. In this segment, we'll take a look at the basic components of a turbine and discuss what each of these components is supposed to do. A major external part of the steam turbine itself is the casing. This one's been cut away so we can see many of the components it contains. This part of the casing is where the steam enters the turbine. It's called the steam chest. Inside the steam chest is the governor valve. The governor valve is used to regulate the amount of steam that is admitted into the turbine. It controls steam flow to the nozzles and is an important part of the overall turbine control system, which we'll talk about later. The steam that has entered the steam chest through the governor valve moves on to the nozzles. As we discussed earlier, nozzles are the components that increase the velocity of the steam. The high-velocity steam from the nozzles is directed onto the first set of moving blades. This causes the blades and the shaft they're mounted on to turn. Then the steam flows through the fixed blades. These blades redirect the steam flow onto the next set of moving blades. This allows more energy to be extracted, so the moving blades and shaft continue to turn. From the second set of moving blades, the steam enters this chamber and is routed on out of the turbine. The shaft and the moving blades are commonly referred to as the rotor. The movement of the rotor is what produces the mechanical energy that can be used to drive other equipment. Bearings are used to help keep the rotor correctly positioned. This turbine uses a thrust bearing and two radial bearings. The thrust bearing prevents movement of the shaft lengthwise along the axis of the shaft. The radial bearings prevent movement of the shaft in a radial direction, or from side to side and up and down. The bearings minimize friction between the shaft and the casing of the turbine as well. Other basic turbine components are located outside of the casing. These external components are most important after the rotor is begun to turn and the turbine is being put into operation. They provide essential support so the turbine can function safely throughout the different phases of operation. In order to put the rotor's mechanical energy to work, the turbine's power must be transmitted to a piece of rotary equipment. A coupling is used to connect the turbine to the driven equipment. For safe operation when the turbine and its driven equipment are running, the coupling should be covered. The coupling cover, or guard, prevents personnel from getting their clothes or fingers caught in the rotating parts. During operation, the turbine must be stabilized so the rotor doesn't move out of its properly aligned position. Bearings, as we've already discussed, help position the rotor. In addition, a pedestal supports the turbine. Mounting the casing on a concrete foundation provides stability, too. Okay, we've looked at a turbine's basic components, including such parts as the casing, governor valve, nozzles, rotor, and fixed blading. In addition to these essential components that you're likely to find in almost any turbine, there are also some typical auxiliary or support devices and systems you need to know about. We'll look at them next. But first, review the material we've just covered. Then answer the questions in your text and make sure you understand what we've discussed in this part of the program before you continue. Earlier, we looked at the major components of a steam turbine, such as the casing, bearings, and rotor. When a turbine is operating, certain auxiliary or support systems must also be functioning. The turbine components depend upon the help of these auxiliary devices to keep the turbine running smoothly. Making sure the auxiliaries are functioning properly is an essential part of safe, efficient turbine operation. To handle this responsibility, you must know what auxiliaries are used on the turbines in your facility and what these support systems are supposed to do. So, in this part of the program, we'll take a look at some common turbine auxiliaries. We'll start with valves. A turbine typically has an isolation or block valve in the steam supply line. You may hear this valve referred to as a throttle valve. There's also an isolation valve in the steam exhaust line. There may be only one block valve located at the header to the steam exhaust. Or, like the turbine shown here, there may be an additional exhaust block valve at the turbine itself. In addition, drain valves are typically used to remove condensate from the casing and piping. Condensate, the moisture that's produced when steam cools and condenses in the piping, can cause serious damage if not removed from the turbine. Drops of moisture that strike the high-velocity blades can chip or pit the blading. So, before steam is admitted and the turbine is started, drain valves are used to remove condensate from the casing and steam chest, as well as from the inlet and outlet piping. The drains and their valves are located at points in the steam flow path where moisture is likely to collect. Also, for the turbine to operate properly, the steam flow through the turbine must be regulated. Two major valves that are used for this purpose are the throttle valve and the governor valve, which we've already mentioned. Some turbines also have nozzles that are operated by external hand valves. The hand valves allow individual nozzles to be selected in or out of service manually for better efficiency during certain situations, like startup or a change in load. High pressure is another factor that makes it necessary to use auxiliary valves. Generally, the turbine casing is designed to handle pressure within certain limits. If the pressure exceeds the design limits, a literally explosive situation could occur and the casing could be damaged or destroyed. To prevent such a catastrophe, most turbines have a safety relief valve. The safety relief valve for this turbine is located in the exhaust line. Some turbines are also equipped with a valve that can warn operators if steam pressure becomes excessive. This device is called a sentinel valve. The sentinel valve provides an audible warning or whistle by allowing a small amount of excessive pressure to leak off. Another common auxiliary device is a steam strainer, which is usually located at the entry to the steam chest. The strainer removes solid impurities, such as corrosion or scale products, from the steam before the steam is admitted into the turbine. In addition, the steam supply line usually has one or more steam traps at low points in the piping. The traps make it possible for the condensate to be removed without allowing the steam to escape. In many turbines, the low-pressure steam, which still has some heat energy, exhausts to a low-pressure header for distribution for other uses in the facility. On the other hand, some turbines are connected to a condenser. In that case, the low-pressure steam is removed under vacuum to the condenser. Now, although all auxiliary components are important to the operation of a turbine, one of the most vital auxiliaries is a lubrication system. This system keeps the turbine's rotating parts from wearing due to friction. The oil in the system also carries away built-up heat from the bearings. Small turbines typically use a ring oil lubrication system. Basically, the system works like this. There's a slinger ring that rides on the turbine shaft and picks up oil from the reservoirs. Then the slinger ring carries the oil along the shaft to the bearings. The system here also includes labyrinth seals. In a labyrinth seal, a series of ridges creates an intricate path called a labyrinth. This path makes it difficult for oil to escape and helps prevent contaminants like steam, dust, or dirt from entering the reservoir. In addition, there's a constant level oiler on each reservoir to maintain the proper oil level during turbine operation. For many small turbines, the bearing housings include chambers called jackets that are used with a cooling water system to maintain the oil at the proper temperature. For each bearing housing, there's usually a line for water into the jacket. This line may include a valve that can be adjusted. Then another line, also provided with a valve that can be adjusted, routes the water out of the jacket, so the water can be discharged after it has been used to cool the lube oil. The last turbine auxiliary we're going to look at in this part of our discussion is called a seal system. The function of a seal system is to prevent steam from leaking past the turbine shaft. Steam leaks out of the turbine are both wasteful and dangerous. They reduce turbine efficiency and can increase operating costs. Also, if steam enters the bearing housings, the steam can condense. Then water will get into the lube oil and degrade the oil's lubricating quality. In addition, leaking steam can burn personnel and make for dangerous working conditions. A major part of a seal system is the shaft seals. Carbon rings are commonly used as seals for single-stage steam turbines. Here, a series of 4 sets of carbon rings are located on either side of the wheel. The rings are installed so that they can come in contact with the shaft. Because the carbon they're made from is softer than the steel of the shaft, the rings wear and have to be replaced routinely. But replacing worn carbon rings is much less expensive than having to repair or replace a damaged shaft. In addition, the carbon rings are fitted in cavities that contain leak-off connections to allow the small amount of leaked steam to be vented to the atmosphere. Well, the valves, steam traps, and lubrication and seal systems we've just covered include some of the major devices that help keep a turbine running safely and efficiently. There are also a couple other auxiliaries that are vital for proper turbine operation. These are the speed control system and the turbine protection system. We'll look at these 2 auxiliary systems after you've had a chance to review your text and answer the questions there. Okay, in the last part of the program, we discussed several of the auxiliaries associated with turbines. Now we're going to take a look at a few additional auxiliary systems that are vital for safe and efficient turbine operation. Some of these auxiliaries protect the turbine and some control its speed. The speed of a turbine must be controlled within the limits that the turbine is designed to handle. If the speed increases beyond the maximum limit and is not controlled, the turbine could literally fly apart. On the other hand, if the speed is too low, the turbine won't provide enough energy to drive the equipment. It's also important that the speed be maintained at a constant level during normal operations. Fluctuations in the speed are inefficient. Hunting is the term used to describe the action when a turbine's control system fluctuates while searching or hunting for the proper speed. In addition, the turbine must be protected from operating under abnormal or unsafe conditions that could seriously damage the turbine, the driven equipment, and related systems in the facility. Various turbine protection devices help prevent this kind of damage from occurring. A governor is the device used to control the steam flow into the turbine and maintain the speed at the desired value without hunting. This is an example of a mechanical hydraulic governor. It has a hydraulic system that reacts to changes in the speed of the turbine shaft. If shaft speed increases or decreases, the governor, through a linkage, adjusts the position of the governor valve in the steam chest so that a constant turbine speed is maintained. As you may recall, the position of the governor valve determines the amount of steam being supplied to the nozzles. And in this way, the amount of steam supplied determines how fast the turbine operates. In addition to auxiliaries for regulating speed, there are also various devices used to protect the turbine during operation. The first of these protective devices that we'll talk about is an overspeed trip mechanism. The overspeed trip mechanism is used to protect the turbine from being damaged in case the turbine speeds out of control of the governor. As you may imagine, a turbine that flies apart due to uncontrolled speed can be very costly to a facility. It also endangers the health and safety of the turbine operators. So it's vital that you have some way to quickly stop or trip a turbine if overspeed conditions develop. Generally, if speed goes beyond a certain limit, a trip valve in the overspeed trip mechanism automatically closes to stop the turbine. There are a variety of arrangements for overspeed trip mechanisms, but they all operate on pretty much the same principle. Basically, if the turbine overspeeds, the shaft's centrifugal force will cause the trip valve in the overspeed trip mechanism to slam shut. When this valve shuts, it cuts off steam to the steam chest and stops the turbine. Also associated with the overspeed trip mechanism is a hand trip lever that the operator can use to trip the turbine by hand. Manually releasing the lever's latch causes the trip valve in the overspeed trip mechanism to shut and stops the turbine. Whenever the trip has been activated, either automatically or by hand, it must be reset manually before the turbine is put back into operation. Some turbines have additional protective devices that will automatically shut the turbine down if an unsafe operating condition develops. These protective devices are commonly triggered by conditions like low lube oil pressure, high bearing temperatures, or some other abnormal condition associated with operation of the turbine, the equipment driven by the turbine, or the system in which the turbine is used. Typically, such devices involve a solenoid trip that is operated by electrical inputs from the system that has developed the abnormal condition. In this example, a turbine drives a pump. If the pump's oil level drops below a certain point, a solenoid trip is activated to stop the turbine. This prevents the pump from being severely damaged by continuing to operate without proper lubrication. By now, you should have a good general understanding of the basic components and functions of a typical non-condensing steam turbine and its auxiliary systems. This would be a good time to look over the turbine you'll be operating in your facility and become familiar with its specific components. After you've done that, you'll be better prepared to look at some actual operation procedures. Also, before going any farther, take some time to review the material in your text and answer the questions there. Then, when you return, we'll begin to discuss turbine operation. We've already covered the basic principles of operation and the major components for steam turbines, as well as some of the typical auxiliary systems that these turbines rely on. For the remainder of this program, we'll focus on the more hands-on routine tasks that operators perform when dealing with steam turbines. Once you have a good grasp of this information, you'll be better able to operate the turbines in your facility safely and efficiently. We'll begin by describing some startup preparations that are appropriate for most non-condensing steam turbines. These preparations include many of the general startup preparations common for any other piece of rotating equipment. Procedures can vary, though, from one turbine to another, and the turbines in your facility may not be exactly like the ones you'll see here. Your company's policies and procedures will likely dictate each specific item to check for the turbines you'll be working with. And, of course, you'll need to inspect the driven equipment and make sure it's prepared for startup, too. What we're going to concentrate on in this part of the program, however, are those preparations that are common for most single-stage steam turbines. Getting a turbine prepared for startup generally begins with an external check of the turbine itself. Look it over for any signs of damage. Make sure that the overspeed trip mechanism has been reset and is in good condition. The trip latch should hold the lever in place to keep the trip valve open until triggered by an overspeed condition. The governor, too, is a vital part of the turbine's control system and ought to be included in your pre-startup inspection. Check the lube oil level for the governor and replace or replenish the oil if necessary. The governor shown here has an oil sight glass which the operator uses to see if there's sufficient lube oil. The glass shows that the oil level is low, so the operator adds oil through the governor's oil filler cap. It's also a good idea to check the coupling and make sure the coupling guard is secure before the turbine is put into operation. One especially important preparation for virtually any steam turbine is to completely drain any condensate from the turbine and its lines before startup. High-velocity slugs of condensate on the rotor during operation can be very dangerous and damaging. To drain the turbine, open the drain valves for the inlet piping, the casing and steam chest, and the exhaust line piping. Then steam is admitted into the turbine by slowly cracking open the block valves in the exhaust line. The turbine shown here has only one exhaust block valve, located at the header. Cracking open the exhaust block valve allows exhaust steam from the low-pressure header to backfeed into the turbine. Doing that not only aids in removing condensate from the turbine and the exhaust steam line, but also allows the turbine to warm up slowly and minimizes thermal shock. Thermal shock is a form of stress that could result from the sudden great differences in the temperature of the turbine's metal and the temperature of the supply steam. This form of stress can lead to metal fatigue and damage to the turbine. Typically, after a few minutes, only steam and no condensate will come from the drains. Then you can close the drain valves and fully open the exhaust block valve. Another major part of startup preparations is preparing the turbine's auxiliary systems. We'll start with the lubrication system. One critical step in checking out this system is determining if the oil level is adequate. In this example, the operator can check the oil level by observing a constant level oiler. He looks to make sure that the glass on the constant level oiler is full. The operator can also drain a small amount of the oil to see that it's clean and not contaminated. Oil that's foamy, dirty, or looks milky, which can indicate there's water in the oil, will probably need to be replaced. To keep the lube oil cool, you may need to put a cooling water system into service. For the turbine shown here, the cooling water is kept circulating through the jackets and the bearing housings even when the turbine isn't operating. One way to determine if this type of cooling system is functioning properly is to feel the cooling water lines and check the water being discharged after it has been circulated through the bearing jackets. If the water lines feel cool and water is discharging, the system is probably functioning properly. Besides draining the turbine and preparing the lubrication system and the cooling water system, you also need to make sure that the seal system is in working order. Any leak-off vents for the seal system should be clear and open. While the turbine is warming up, look at the turbine shaft where it penetrates the casing. If the seal system is okay, there shouldn't be an excessive amount of steam leaking past the shaft to the atmosphere at these locations. After a sufficient warm-up period, which is usually stated in your facility's operating procedures, the turbine startup can begin. First, slowly open the throttle valve to bring the turbine speed up to about 10 to 20% of the normal speed. This part of the startup is often referred to as heat soaking. It allows both the rotating and stationary parts of the turbine to come up to normal operating temperature evenly. Company procedures usually dictate how long the turbine must heat soak before you can continue the startup. After the heat soaking period, the turbine can be brought up to normal operating speed. In order to bring the turbine up to speed properly, the operator must slowly open the already partially open throttle valve. He watches for movement of the governor linkage. And he also listens for the sound of the increasing turbine speed to level out. These signs indicate that the governor has taken over and is in control. Once that occurs, the operator can fully open the throttle valve. Opening the throttle valve all the way before the governor has control could cause the turbine to overspeed. In turn, this would trigger the overspeed trip and stop the turbine. If the governor doesn't take over when you're attempting startup, let your supervisor know so the problem can be corrected before the turbine is allowed into operation. Once the turbine has reached normal operating speed and you've verified that the governor is working properly, the startup procedure is essentially completed. However, an operator's responsibilities certainly don't end with getting the turbine started. There are conditions that must be observed and monitored while the turbine is running. We'll look at operator responsibilities during normal turbine operation when we return. So far in our discussion of turbine operations, we've got the turbine started and running at normal operating speed. When the turbine and the equipment it's coupled to are both running smoothly and the driven equipment is performing the work it's supposed to do, the turbine is said to be operating normally under load. Generally, this is the phase of turbine operation that you'll deal with most. Other phases like startup and shutdown occur less often. But making frequent checks of the turbine and its auxiliaries throughout the time that the turbine is operating under load is likely to be one of your routine tasks on the job. In order to keep the turbine running the way it's supposed to, it's important that you perform these checks properly. During these inspections, you should observe whether the turbine appears to be running smoothly and whether the values of the readings and overall operating conditions are normal for the turbine that you're working with. You should note any unusual noise or circumstance associated with the turbine, its auxiliaries, or the driven equipment. Checking out possible problems early is a good way to prevent more serious trouble later. The operator shown here is checking the level on a constant level oiler to determine if there's enough lube oil in the oil reservoir and if the oiler is working properly. The level in the glass is slightly lower than it was at startup, which is generally a sign that the constant level oiler isn't plugged and is maintaining sufficient lubrication. Adequate lubrication helps keep the bearings from overheating. Likewise, the bearings could get too hot if the cooling water system isn't working the way it's supposed to. For this reason, the cooling water flow must also be checked regularly. On this turbine, the operator can feel the cool water flowing through the pipes into the turbine. If the lines feel cool, that's usually a good indication that the system is functioning properly. He can also observe and feel the cooling water being discharged after it has passed through the turbine. A steady discharge of water generally means that the system is okay. While the turbine is in normal operation, readings of turbine speed help you judge how well the governor is working. The speed for the turbine shown here is indicated in RPM on a tachometer. Another condition that is important to observe during routine inspections is vibration. It's normal for some small amount of vibration to be present anytime a turbine is running. Excessive vibration, however, can be an indication of trouble. Two ways to detect excessive vibration are by listening for unusual noise and by looking or feeling for abnormal vibration at the governor, bearing housings, turbine casing, and the coupling. Your facility may also have special vibration monitoring or analysis devices. If so, refer to your facility's operating procedures for instructions on how to use these instruments. In addition to making these routine checks, an operator must be alert for signs of any abnormal conditions during turbine operation. Regardless of the exact type of steam turbine you're operating, there are some abnormal conditions that you need to check for in most cases. In the turbine's speed control system, hunting and overspeed are conditions to watch out for. Hunting, as we discussed earlier, is inefficient. Trips from overspeeding are also disruptive and costly. Although, of course, if the trip mechanism weren't working to stop the turbine during overspeed conditions, the cost of the facility could be even greater. Observing the operation of the speed control and the turbine protection systems during your routine inspections can help you determine if the turbine is running normally. When the turbine's running correctly, the RPM for the shaft speed is normal and steady with no hunting. Also, when the turbine is running the way it's supposed to, it makes a distinct sound that's unique to that turbine. You'll need to become familiar with the normal operating sound of the specific turbine you're working with. Then you'll be able to tell if the turbine doesn't sound like it's running properly. Finally, when the turbine is operating, pressures for the turbine casing and for the steam going into and coming out of the turbine may need to be monitored. A steam turbine relies on the maximum pressure difference between high inlet and low exhaust pressures to do the best or most efficient job of producing rotary mechanical energy. Excessive exhaust pressure is usually a sign that the turbine or the steam system it discharges to is not operating as efficiently as it should. Also during operation, pressure can build up in the casing. Some turbines have a sentinel valve, as we saw earlier, that gives an audible warning when casing pressure becomes too high. And almost all turbines have a safety relief valve in the exhaust line that will open to protect against excessive pressure. If the safety relief valve isn't functioning, other corrective actions must be taken. You should check your facility's operating procedures to find out how this problem should be handled for the turbine you're operating. Well, by now you'll probably agree that an operator has a lot of responsibilities to take care of when a turbine is operating under load. He has to make sure the turbine's being adequately lubricated and cooled, that it's not overspeeding or hunting or vibrating excessively. And he has to make sure that all the auxiliary systems are functioning the way they should to keep the turbine operating safely and efficiently. Eventually, however, a turbine will have to be stopped or shut down. An operator has tasks to perform during this final phase of turbine operation too. We'll look at shutdown procedures when you return, but first, review the material in your text and answer the questions there. In our discussion of steam turbine operation, we've looked at preparations for startup, and normal operation under load. There's still one last phase of turbine operation that we need to talk about, namely shutdown procedures. Dealing with normal operations under load is more likely to be part of your daily routine. But shutdown is an essential phase of overall turbine operation, and it's vital that you be able to perform this procedure properly whenever it's necessary. Basically, a shutdown means that the turbine is stopped and taken out of service. During a normal shutdown, this is done as simply a planned part of routine operations. On the other hand, an emergency shutdown is one that is not planned for and occurs whenever a turbine must be stopped quickly, usually due to abnormal conditions or emergencies in the turbine, its auxiliaries, the driven equipment, or to problems elsewhere in the facility. The specific steps for a normal shutdown can vary from one facility or turbine to another. The procedures we'll cover apply to most cases, but you should check the operating procedures for your own facility to be sure you know exactly how the turbines you'll be working with are shut down. In some cases, the first step is to manually trigger the overspeed trip. This shuts off the steam supply and allows the turbine to coast to a stop. It also tests the manual trip mechanism. Then the operator proceeds with the shutdown by closing the throttle valve. Now, not all turbines are shut down using the manual trip. In fact, the trip lever isn't used at all to shut down this particular turbine. Instead, the operator begins gradually shutting the turbine down by partially closing the throttle valve and bringing the turbine to a slow roll. He lets the turbine rotate slowly like this for a brief period, specified in his facility's operating procedures, typically 2 or 3 minutes. This provides a cool-down period for the turbine. After this cool-down, the operator can then completely close the throttle valve. He follows a similar procedure for the exhaust line. He closes the exhaust block valve and opens the drain valve in the exhaust piping. Regardless of whether your turbines are shut down using the manual trip or not, you'll also need to take care of any auxiliaries that require shutdown attention. This may include cutting off the cooling water system or turning on an auxiliary oil pump for a lubrication system. You'll need to check the exact procedures required for the turbines in your facility. After the auxiliaries have been attended to, the operator opens the drains for the casing. This helps prevent water from collecting in the turbine. Finally, you'll need to perform whatever shutdown steps are required for the equipment that is driven by the turbine you're working with. Normal shutdowns, like the examples we just saw, are the kind of shutdown procedures you'll be using most often. Situations can occur, however, where there's no time for a gradual normal shutdown. Instead, an emergency shutdown must be performed to safely stop the turbine as quickly as possible. To accomplish this, simply trigger the overspeed trip by hand. Then, as soon as the situation permits, you can complete taking the turbine, its auxiliaries, and the driven equipment out of service just the same way as it's done for a normal shutdown. Properly shutting down a turbine is an important operator responsibility. It's vital as well that an operator be able to handle typical operating problems. Knowing how to handle these situations can help you prevent your turbine from being severely damaged or having to be shut down. So when you return, we'll look at some common operating problems you might have to deal with when you're working with turbines. First, though, take some time to read the material in your text and answer the questions that follow. During the last few parts of this program, we've talked about operator responsibilities during the various phases of turbine operation and about some abnormal conditions to especially watch out for, like water getting in the turbine or abnormal lube oil flow. For the final part of our discussion, we'll talk about how to handle some typical operating problems before they develop into trouble serious enough to damage or shut down the turbine. As we mentioned before, many problems in turbine operation eventually show up as excessive vibration. This condition can be caused by problems in the turbine, the coupling, or the driven equipment. Sometimes you can hear the vibration and tell if it's coming from the turbine or the driven equipment. But some vibrations may not be able to be detected by listening for them. Generally, your sense of touch is a better means of identifying and locating the source of the vibration. Also, some facilities have special devices for vibration monitoring and detection. In any case, let your supervisor know if you find that the turbine or the driven equipment is vibrating severely. The turbine may have to be shut down to prevent damage. Then the problem that's causing the vibration will have to be identified and corrected. Other operating problems are related to speed and involve the operation of the turbine's speed control system, including the governor and the overspeed trip. If the governor is hunting, examine the linkage to make sure it operates smoothly and isn't binding. Also, check to make sure there's a sufficient amount of lubricant for the linkage. Sometimes, an otherwise normally running turbine may hunt when its load is higher or lower than normal. If your turbine is equipped with hand valves, you may be able to use them to eliminate the hunting. How you would use these valves depends on whether the turbine is operating under a high load or under a low load. For high load, you'll need to open additional hand valves slowly, one at a time, until the speed is steady and the governor has regained control. For low load, you'll need to slowly close additional hand valves one at a time until the governor regains control and the speed remains steady. In other cases, the speed of the turbine may be steady, but too fast or too slow. The turbine may run too slowly if the inlet steam pressure is too low, or if the back pressure is too high, which can cause the safety relief valve to open. It's possible, too, that there simply isn't enough steam available to provide the steam pressure needed, or the turbine's overspeed trip valve isn't opening fully. Generally, when the turbine speed appears to be lowered because of problems with the steam pressure or supply, you should notify your supervisor about the situation so it can be handled in the manner that's appropriate for your facility. In addition to low turbine speed being a problem, you may also be confronted with the problem of high turbine speed. A number of different causes, like high inlet or low exhaust steam pressures, for example, could make the turbine speed be steady but too fast. If you find that the turbine you're working with is running at too high a speed, tell your supervisor so the condition can be dealt with according to the operating procedures for your facility. Other turbine speed problems involve the operation of the overspeed trip mechanism. The overspeed may trip too soon. That is, it trips too close to the turbine's normal operating speed. If this happens, check to see that the trip latch is holding the lever securely in place. On the other hand, the overspeed may trip too late. In this case, the overspeed isn't triggered until after the set speed for a trip has been exceeded. If this problem occurs, check to make sure the trip latch isn't stuck. If the trip latch is okay, but the turbine is tripping too soon or too late, the overspeed setting may be incorrect, or the cause of the trouble may be in the trip pin assembly. In either case, you should let your supervisor know about the situation so it can be checked out and corrected. Also, let your supervisor know if the overspeed is tripping, but it isn't stopping the turbine. That could mean there's a problem with the overspeed trip valve, and the turbine may have to be shut down so repairs can be made. Well, by now you should have a pretty good idea of what a non-condensing steam turbine is, how it functions, and what an operator is responsible for during the various phases of turbine operation. We've described a steam turbine's basic components and their functions. We've looked at the various auxiliary systems that support, control, and protect the turbine. We've discussed basic operator responsibilities during the various phases of turbine operation. And we've looked at some typical problems you could encounter during turbine operation. Understanding this material will help prepare you to safely and efficiently operate the turbines you'll be working with on the job. In turn, properly functioning turbines can help minimize downtime, prevent damage, and contribute to the overall productivity and efficiency of your facility.